Hi everyone, hope all of you are doing very well. In our previous lecture, we discussed the preparation of alcohols from carbonyl compounds, and as a substrates in that reaction, we took aldehydes and ketones. From aldehydes and ketones, the reduction of these two carbonyl compounds give us the alcohols. So we looked in the mechanism of the reaction also. Okay, so in this reaction we are going to take yet another another reaction for the preparation of alcohols, and that's the reduction of carboxylic acids and esters. Okay, so the carboxylic acids and esters are yet another important the class of carbonyl compounds. Okay, if we try to represent, so the general representation of carboxylic is acid is Rc double bond OH. Okay, or we also write it RCOOH. And for the ester we can write, we have Rc double bond OR. Okay, these are two ester groups, these are two R groups for in it. So we have R, we can also write as RCOOR. The R dash here represents that it can be a different alkyl group, it can be a different R group. So this is the general representation. So if we look at the both of these carbonyl compounds, we have the carbonyl group present in them. So this presence of this carbonyl group makes them reactive also. So we can also reduce the two groups of carbonyl compounds. So in this video we'll try to look at the reduction of carboxylic acids and esters. Okay, and we also look at the mechanism how the conversion is followed. So if we reduce carboxylic acids, we get primary alcohols. Here we have the example, and the reduction is done. Done by the strong reducing agent lithium aluminum hydride. LAH is a short form to write this lithium aluminum hydride. Okay, so this reducing agent is used. This is the strong reducing agent, and the strong reducing agent means that it very easily gives the hydride ions. H negative ions are easily given out by these reducing agents. Okay, and H negatives are, they are nucleophilic in nature. Okay, so the reduction of carboxylic acids gives us the alcohol, the primary alcohol, and we have the water as the byproduct. And if we try to reduce the ester, so each molecule of ester gives us two molecules of alcohols. Okay, two molecules of alcohols are obtained by the reduction of each ester. Okay, again the reduction is done by the reducing agent, that's lithium aluminum hydride. We are using the strong reducing agent again, and we have to remember that because the ester and the carboxylic acids, the carbonyl compound, these two carbonyl compounds are less reactive towards the nucleophiles. Okay, than aldehydes and ketones, they are less reactive. So we only use a strong reducing agent in these cases. Okay, we cannot even use the sodium borohydride for the reduction. So in each reaction we have two hydride ions are added to the carbonyl. Okay, carbonyl compound, either esters or carboxylic acids. We have two hydride ions which are attached. Okay, so we'll be explaining the mechanism of the reaction, and in the mechanism we will be clear about how the reaction goes. Okay, we have to remember that here we get two alcohols. One is from the acyl part and another from the alcoholic part. Okay, we'll look at these aspects of the reaction in the mechanism. So first of all, we'll try to discuss the reaction mechanism of carboxylic acids. This is a general carboxylic acid. Okay, so in this we have the reagents. In the first step we are using the reagent, we are using the reducing agent. Okay, and the reaction goes in the ether. This is the solvent, of the reaction. So this and in the second step we have the acidic workup. That is, we add the proton to the required positions. We have the acidic workup in the second step. Okay, so in the reaction we get the alcohol. Now looking at the mechanism, so in the first phase, first step of the reaction, what happens, the reducing agent gives the hydride. This produces the hydride, and hydride is the nucleophile. Okay, so the first reaction is the nucleophilic attack of hydride on the electrophilic carbonyl. Okay, that also on the carbon electrophilic carbonyl carbon. So because there is small negative charge, and there we have small positive, and here we have small negative charge, so this is going to attack on the electrophilic carbonyl group. So the electron pair is going to shift towards the oxygen, and in this step we get the alkoxide. This is the alkoxide intermediate we are getting. But this alkoxide ion is unstable. So for stability, what happens, well, the electron pair from the oxygen is going to form the pi bond between the carbon and oxygen, because there is a possibility of formation of this pi bond, because we have a very good leaving group. Here. So because OH negative, the hydroxyl group is a good leaving group. Okay, this is very good leaving group. Therefore the electron pair comes and is the formation of double bond between carbon and oxygen, and in this step we are getting alcohol. Sorry, this is aldehyde. Yet another we have the carbonyl compound. Okay, and from here the reaction mechanism is going to mechanism going to follow as we have shown for the aldehydes, reduction of aldehydes by the metal hydrides. So again there is a nucleophilic attack of hydride ion on the carbonyl carbon, and the electrons are going to shift towards the oxygen. Okay, so we have a negative charge here. So now this negative charge will be of the oxygen will be stabilized by the acidic workup. Here we have the acidic workup, we have the protonation. The proton from the medium comes and attached to the oxygen of the alkoxide ion, this alkoxide ion. Okay, and as a result we get the alcohol. Look, we have shown the colors. Here we have two hydrides, two hydrogens that have come from the hydride, and we have this hydrogen that's attached to the oxygen that has come from the acid which is present in the medium. So in overall reaction we have used two hydrides, and we have used two protons. Okay, two protons in the reaction. So this is the overall reaction mechanism of the reduction of carboxylic acids. Okay, this is the general this is the same representation of this molecule. We can also represent this alcohol as this. Okay, so we have taken the general example. In the next slide we'll be discussing about the reduction of esters, and it's going to follow the similar mechanism, but there are little changes there, that we here in the reduction of esters we are getting two alcohols. Okay, we have two alcohols here. If you look, we have two alcohols in the as a product of the reaction of the reduction of an ester. Okay, how the reaction goes, we have similar mechanism. In the first step there is the nucleophilic attack of hydride on the carbonyl carbon, and the electrons shift from the pi bond shifts towards the oxygen, and the alkoxide ion is formed. Okay, so again this is unstable, so the electron pair on the oxygen is going to form again the pi bond, double bond between the carbon and oxygen, and in this step the OR group is going to leave, because again this is the good leaving group. We will be getting OR negative in this step, OR negative. Okay, but this OR negative will take the proton from the reaction to get stabilized, and as a result we get the first alcohol of the alcoholic product of the reaction. Okay, with the first alcohol HOR negative, or we can also represent this as ROH. Okay, so this is the first alcohol that we're getting, and also we get an aldehyde in the step. This is an aldehyde. Okay, now there is again the nucleophilic attack of hydride. Another hydride ion is going to attack on the carbonyl carbon, and again there is a shift of pi bond towards oxygen. Again we get the negative charge on the oxygen. Okay, and now we have two hydrogens on this carbon. On carbonyl carbon, we have two hydrogens that have come from two successive attacks of the hydrides. Okay, now to stabilize this negative charge, we have only option, that's to protonate this oxygen. So this is the acidic workup of the reaction. So the oxygen will take the hydrogen from the reaction medium, and the required alcohol is going to form. This is the second alcohol molecule that is formed in the reaction. Again, you should notice the colors, that we have obtained two hydrogens from the reducing agent lithium aluminum hydride, and the oxygen that's attached to the oxygen, no, sorry, the hydrogen that's attached to the oxygen, that comes from the proton, the acidic medium, the proton that's present in the reaction medium. And this again is the same representation. Okay, we can also represent this molecule as this. So in this lecture, we have discussed the reduction of esters and carboxylic acids. Another important reaction is the production of the alcohols from the esters by using some different reagents. Okay, this is called as Bouveault-Blanc reduction, in which we use sodium as a reducing agent in alcohol. Okay, so sodium in presence of alcohol reduces esters to again two alcohols, as in the case of reduction of esters by LAH, we get two alcohols. Similarly, by the reduction of esters, we get two alcohols. Okay, this reaction is industrially important. Okay, we have got the industrial importance of the reaction. So we may be asked some questions from this reaction also. We'll be asked, we will be given with the reaction, and we have to write the name of the reaction. Maybe we'll be asked the name of the reaction, or we'll be given with we'll be asked which of the following are the reagents that we use in the Bouveault-Blanc reduction, or we can be asked the Bouveault-Blanc reduction is important for which type of carbonyl compounds. So we have esters, or we'll be asked what are the products of the reduction of Bouveault-Blanc reduction. So we'll be having two alcohols as a product. Okay, so the reaction is industrially important. We don't need to look at the mechanism in this reaction, although mechanism is very simple for it. Okay, another industrially important reaction is the catalytic hydrogenation. Catalytic hydrogenation of carboxylic acids, RC double bond OH. We can catalytically hydrogenate, that is, we are using hydrogen in presence of the catalyst. Can be a palladium, it can be a platinum, it can be a nickel, and we have to give the extreme temperature, almost more than 200 degrees Celsius for it. Then we can get the required alcohol. Okay, again, we can also reduce catalytically, we can reduce the esters also, and we'll be having the same reagents. Okay, we'll be having the heat and also the same reagents, and in this reaction we'll be getting two alcohols. Okay, we're getting two alcohols, ROH. This is dash. Okay, so these are the two reactions which are industrially important. Okay, as we have seen, other carbonyl compounds can also be reduced by the catalysis. Okay, we also do the catalytic hydrogenation for acid chlorides. We can do it for the aldehydes, ketones, and all of them yield the alcohols. Okay, but these two are efficiently reduced by the catalytic hydrogenation process. Okay, in the next video we'll be trying to solve some problems which are based on this reaction, and we'll also try to revise some more concepts while solving the problems.